Good morning, forest soils. Good to be here. I'm not with you. You're getting this kind of delayed. I'm live up here with my head in the clouds and delivering this lecture. I'm actually at an international conference in Turkey presenting, and so I can't be two places at the same time. Not yet. I'm working on that. So we're ready for our next topic, and it's soil acidity. This is our last topic just before we hit nutrition. And of course, this week you'll be doing this in lab. So this, as we hit into Monday afternoon, you'll be pretty familiar with this material. So some reminders of things that we need to remember. Exam 2 is Wednesday. You probably haven't forgotten that. I'm sure you're all studying very hard. The pH lab is like all our other indoor labs. It's in 102 Walters. This is our last bench lab. The next one's just calculations. It's quick, but it's complicated. Okay, so you'll have to pay good attention to your teaching assistants and lab instructors. And so that's the announcements. Last time, what did we do? We talked about CEC. We mentioned determination. It's operationally defined, so the methods determine the results. We also talked about weathering intensity. We talked about a weathering intensity in reaction with CEC, with clays becoming progressively more weathered and CEC dropping out. We then brought into a discussion of genesis of clays. Right? And then we left off talking about CEC, two different operational methods, buffered versus unbuffered. So I'll mention a little bit again, and we'll go over some of this, and we'll kind of review it quickly as we get into soil acidity. So we'll clean up all these little, let's say these may be problem areas or question areas or maybe complicated areas. And we did balance and CEC reactions. I asked you to take one home with you. Okay? We talked about flocculation and dispersion. And so the prelude to acidity is this slide, right? And so this is, what am I looking at here, right? So you can, this is little p, h. And so we're going to be using this as a calculation this week. So what do we have here? We have a log, negative log, and you must recognize this. Anybody, any good musician would know a bass, and negative log, base 10. And so this is kind of a picture of pH, an abnormal picture. And so here is written what pH is. pH is the negative log, base 10 of hydronium ion activity, H plus activity. Right? And so this little p, okay, it stands for minus log base 10. Okay? H stands for the concentration, the activity of hydronium. And that's the formula. It's a very simple, straightforward formula. And you could, that's also equal to 1 over log 10 of hydronium activity. Okay? And so this is the definition of pH. You're going to use that, compute that this week, look at concentrations and activities. That's the subject of the first part of the lab this week. Okay? So there's negative log base 10, hydronium ion activity. We usually talk about concentrations, but it's really technically an activity. And so every time I talk concentration and don't stress activity, the chemists kind of beat on me. So this is activity, and we think about it in terms of concentration. Hydronium, H3O plus, this protonated water. What's log, right? So remember back in high school, or maybe in grade school for some of us, or maybe your first year of chemistry, you talk about what a logarithm is. It's an exponent, right? So log 10 of 100, okay? What's that equal to? 2, right? 2 is the exponent. 10 to this 2 is equal to 100, okay? So the logarithm of 100 base 10 is 2. Fairly straightforward. What is the log base 10 of 0.01? Okay? You'll have to stretch your mind a little bit and go back to just some very simple math. Right? That's minus 2. Right? 10 to the logarithm minus 2, the negative log, is equal to 0.01. It's a very simple, straightforward way to use logarithms. It makes calculations easier because you can express orders of magnitude in a single number. Very convenient. Back in the day before calculators and slide rules, this was the way to calculate things and make things more efficient. Now, of course, just punch in a calculator, voila, you're off and running. So let's think about that in terms of the width of these pH ranges, and let's consider pH 3 versus pH 7. Right? So what does pH 3 mean? And so go back to that equation. pH 3, the hydronium ion activity, okay? Or the concentration, H plus per liter. What does pH 7 mean? Same thing, 10 to the minus 7, 10 to the minus 3. So 1 pH unit, 10-fold difference in hydrogen ion activity. Right? So we go back and fill that in. Here we have pH 3. That means the activity is 10 to the negative log, 10 to the minus 3. And what's 10 to the minus 3 in the decimal? 0.001. Let's look at pH 7, 10 to the minus 7. Okay? There's only 4 difference in units, but 10 to the minus 7, 1, 2, 3, 4, 5, 6, 7. That's 0.0000001. Okay? That's 7 orders of magnitude difference in change in concentration or activity. And it's just pH going from 3 to 7. That's a big difference, right? A big difference. So pH, 1 unit is a vast difference. 2 units is 100. 3 units, 1,000. So these are units, they seem like only 1 pH unit, but it's very different. And so ask me why I care. Why are we worried about pH? And here's a nice way to think about that. What is pH control? pH is very much correlated with plant growth and where plants can do well. Here's from the figure 926 in the text. This shows various herbaceous plants and the range of soil pH where they do all right. And so if we look at the alfalfas, they're over here in the range of 6 to 7 and neutral to slightly acidic. And that's where they grow. So you have very acid soils, you can't produce alfalfa. Then we go down to a variety of soils. We get down to some of the other plants, the acidic loving plants, and they're down to lower pH. So pH is just so easy to measure, and it's a major important determinant of how plants get their nutrition and where they exist. If we look at a specific plant, here's a plot of red pine seedlings, right, and soil pH. And this is a little experiment, a greenhouse experiment. And so as the pH increases, note the rapid drop in seedlings height. Okay? When you get to the high pHs, it's deadly for red pine and many conifers. They can't exist in higher pH situations. So the productivity of species is very much dependent on pH. That's why we care. And why does this all happen? So if we look at soil acidity pH, we're talking about active acidity. Here's the range. Here's pH going from 4 to 9. And fungi, pretty much, they don't get too worried in the acid systems, and they're across these systems. Bacteria, on the other hand, they start to drop off tremendously as acidity increases. The pH drops. Many of these nutrients are very much affected. Their solubility, their availability is affected by pH. And then we have things that are high concentrations at low pH. So pH is a driver of nutrient solubility and availability. That's why we care about it. Okay? And so it's so easy to measure, and it's such an important variable to give us so much information. That's why we bother. That's why I care. So let's look at the range of pH. Here's a range going from 0, which is extremely acid, up to alkaline, 14, right? And so battery acid up here in the less than 1 pH. Okay? And then we go to lemons and vinegar and so forth. We get milk up here around 7. We get into antacid tablets. So this is a range of things that common products that we're used to thinking about in terms of the pH scale. Okay? Strong acidity, we think about below 5. And we think strong alkalinity above 8.5. And then we think about the ranges where we see these. So we have some very acid sulfate soils that have very low pH. And we have some acid peats, and we start to see increases. Forest soils in this range, okay, humid regions, calcareous soils. And so you start to get a feel for maybe there's some link of this with soil genesis and classification. And note, pH about 4, 4.2 for beer and coffee. Now, it's not inconsequential that that's the same pH range, the midpoint of forest soils. So I rest my case. And so H+, it's in solution, it has a lot of activity. The question is, where the H+ does it come from? Or why is it in solution? What makes it available? And that's a subject of part of the understanding where these things are driven from when we measure pH. And so let's think about the source of H+. And H+ is from protonated acids. And we have a lot of inorganic acids, right? There's everything from sulfuric and nitric, and a very common one in soil, carbonic acid, H2CO3. And so why do I talk about this so much as one of the important inorganic acids? When you dissolve carbon dioxide in water, you get carbonic acid. And so there's a lot of CO2 in soils is that produced with respiration. You dissolve that, and so carbonic acid is rather common. How does carbonic acid work? So here's H2CO3. It dissociates, it pushes off a hydrogen into solution, and then it's balanced by a bicarbonate anion, right? HCO3 minus. This is a bicarbonate. So when you first think about the dissociation, you don't have H plus in solution. The first thing that happens is you get H plus accompanied by the bicarbonate anion. That's the source of this beautiful inorganic acid, hydrogen pushed out into the solution. There are organic acids, and we represent organic acids with R for this big long C this, C that, carbon, carbon, carbon. And the working chain of these acids, this is carboxylic acid. Right? So we talked about carboxyl groups. Okay, so carboxyl groups are one of the working ends of organic acids. And so you get a dissociation of H from the hydroxyl group. And this is remember that we talked about the double bond and the OH. So the same things we talked about in soil colloids kind of apply here to these organic acids. This is one of the business ends of organic acids, the carboxyl group. Organic, carbon-based. Inorganic, not carbon-based. Okay? Organic, carbon-based. So we can measure the strength of these, and you learned this back in Chemistry 1, something called the pKa. Okay? And the Ka, this is the dissociation constant for an acid. K for dissociation, A for acid. P, same as in pH, the negative log. Right? So the pKa of an acid is the negative log of the hydrogen ion concentration, okay? And the product with its anion divided by the total. So let's look at this. This says that we have H plus a little bit, and we have the anion, the balance in anion, bicarbonate, and we have a whole bunch that is not dissociated. Okay? So as more and more dissociates, this dissociation constant gets bigger and bigger. Right? But since we're dealing with logs, the numbers, okay, change accordingly. So the Ka for carbonic acid, a measure of its strength, is 10 to the minus 6.35. Right? The pKa, what's the pKa? What's the negative log of that? 6.35, right? Negative log. So this is a weak acid. Okay? When you get pKa's with little contribution below 5, that's weak. And so think about what this Ka means. This means that 10 to the minus 6.35, this little tiny bit, is in dissociated form as a proportion of the total. Okay? So the more negative this number, the more negative this number, the smaller this, the bigger the pKa. So big pKa's, little dissociation. So when we get the pKa's 3 to 5, that's more in the organic acid range. Organic acids make a greater contribution to hydrogen in acid soils than carbonic acids, some of the inorganics. Okay? So that's worthy of noting that these organic acids, they're relatively ubiquitous here in our humid systems. They're very important, they're big contributors to acidity. The concentration, 10 to the minus 3 to 10 to the minus 5, right? The pKa, 3 to 5. So just keep that relationship in mind, and it'll be very helpful to understand when we have big pKa's, little dissociations, weak acids. Small pKa's, a lot of dissociation, strong acid. So let's do a retention check. Large pK, strong or weak acid? I can't call on you, so I just have to assume that you're thinking about it. Right? So large pK is a weak acid. Think about aluminum. aluminum is ubiquitous in our soil systems, right? We have aluminosilicates. It builds up over time. It's one of the big players. And so we spend a lot of time thinking about how it influences soil acidity. It has a big role. And this kind of expresses it. When you have aluminum +3, which is an acidic system, this is very common. It's soluble as +3 ion. And it comes into contact with water. It hydrolyzes water. So we get H2O split off an H+. You'll note that this is a proton, and this contributes to acidity. Okay? And so when that aluminum +3 does that, we end up with aluminum OH2, okay, +2. And we have this hydrogen ion is now out in solution. The pKa of this is around 5. So that AlOH +2, now it also contributes hydrogen. So this, when it hits water again, splits it, hydrolyzes water. Now we get AlOH2, 2 of them, +1. Okay? So we've generated another H+. We continue going, and we have AlOH2+. Okay? It generates an H+. At this point, we're getting toward neutrality, and gibbsite precipitates out. And then aluminum is pretty much done contributing to acidity when you get to neutral. So acid conditions, Al +3 is generating H+. Little less acid, the AlOH2+ is generating it. And a little closer to neutrality, the AlOH2 +1. All this contributing to H+ to the soil solution. So you can see that the role of aluminum is to hydrolyze water and push out H+. So we could say that aluminum generates acidity by hydrolysis. And think back to that chain, Al +3, AlOH2+, AlOH2 +1. And so that also connect with the pH, right? Aluminum +3, this is the dominant portion at low pHs, right? Aluminum +3, low pHs, that's kind of the same thing. That produces H+. As you get little less intense acidity, higher pH, AlOHN dominates, okay? And N being 1 or 2. And then the middle pH ranges, you're still getting H+. Think back to that diagram, H+ generated. Non-acid cations dominate at high pH. Right? And so then you get gibbsite. And so now no more aluminum, and then we get the higher pHs, aluminum's out of the picture. So think back to last week when we talked about pH and we talked about our exchangeable cations and effective cation exchange capacity. We showed this graph of soil pH and effective CEC. As the pH increases, effective cation exchange capacity increases. Okay? Some of that's permanent charge, and this is pH dependent. When you get very acidic, most of that is taken up with bound hydrogen aluminum. They're tightly held to the micelles. Aluminum ions and exchangeable cations, they start to increase. Okay? And as you get past 6 and 7, you're into exchangeable non-acid cations. They don't generate H+. Effective cation exchange capacity. Organic soils, all that charge is effective CEC. Right? And as we get higher and higher pHs, the exchangeable non-acid cations increase. Hydrogen and aluminum are bound here, and as you increase the pH, they become less problematic, less soluble. Effective CEC. And we spent some time talking about what effective CEC was. It's done at the pH of the soil. So CEC, some of exchangeable cations the soil can absorb. This is review. Effective CEC, the exchangeable cations the soil can absorb at the pH of the material. Again, just we're reinforcing what we talked about last week. And we use this diagram showing effective CEC. And we had organic colloids, and here were some of the inorganic colloids, smectite clay, the silicate clays, and kaolinite clay. So this diagram is familiar to us. What does it mean? If we measure the pH at 5, right, so we get on here pH 5, measure the CEC, and so for organic material, that would be about 120 centimoles of charge per kilogram. And above the pH-dependent charge, okay, if we look at smectite, it has very little pH-dependent charge. And so we have pH increasing the organics. They're going wild. If I measure the CEC at pH 7, okay, I get a different answer. We have some pH-dependent charge, but that pH-dependent charge is huge for humus, right? We're up around 210 centimoles of charge per kilogram. Okay, so this again, effective CEC determined at the pH of the soil. And this shows the magnificent change and the magnificent impact of organic material on CEC compared to this smectite, which is a silicate clay. Pretty cool. So when we force a higher pH, when we use a high pH system, what happens to CEC? And you remember, when we're going to force the pH 7, we're going to get a bigger CEC. So methods matter. Bigger number. And you remember how we got this, right? Remember how we did pHs with, not pH, remember how we did CEC. We leached the sample with ammonium solution. We pushed everything off, okay? And on the exchange sites, we ended up with just ammonium. We pushed that ammonium off, replaced it with K, and we measured the concentration of the ammonium here. And that was part of our CEC determination. Okay? Just again, review. And so let's think about doing that. We talked about using effective CEC. To do that, we use a neutral salt. So a neutral salt and ammonium chloride. So we'll pour ammonium chloride. Of course, we're not affecting the pH of a solution. We mix it up. We have ammonium and chloride. We drip that through the soil. And that's whatever the pH of the soil is. Maybe that's soil pH is 5, maybe it's 4. Whatever it is, the exchange takes place at that pH. We haven't adjusted it. That gives us our effective CEC, exchange at the native pH. Effective CEC. Okay. Commonly used neutral salt, ammonium chloride. And why? So back in the days of the acid rain work, when I was a postdoc, we had issues. We really wanted to represent the CEC of the soil as it occurred, not as if someone forced it to 7. In ag systems, most of our work centers around 7, 6 to 7, because that's where the maximum availability is of nutrients. We're in forest soils. It's rare in the Northeast to have such high pHs. So we wanted pictures or understanding of CEC at the native soil pH. And that's why this whole thing developed around effective CEC and using ammonium chloride. Largely that need from some of the acid rain research, which I cut my teeth on as a postdoc, and it was a good way to get some research. So buffered extracts. So we talk about the buffered methods, not effective CEC, but CEC. And many of these will push that pH up to 7 or 8.2. So we'll mix up our solution for ammonium acetate. We'll jack the pH up to 7 or 8.2, and that's going to be the solution we'll use. And so when we do that exchange, we're forcing the exchange at that high pH of that extractant. Commonly used buffered extracts. The most common one of them is ammonium acetate at pH 7. So here's ammonium, here's the acetate anion. Okay? That's one of the most common ones used in labs. We push it at pH 7. And as I said last week, if we want to compare a wide range of soils across the country at different pHs, kind of on the same basis to get their CEC, we'd use this simple one way to do it is to push it at pH 7 and measure everything at that pH. Another one that we use is barium chloride with triethanolamine. Okay? And so that's called TEA at pH 8.2. Again, barium chloride being the salt, we push this up to pH 8.2, and we can compare across a wide range of pHs. Okay. So, soil acidity, conceptual model of it. Let's think about that. Okay. And so the way to think about that is in pools. And so we think about 3 different pools. And so the first pool, we talk about active acidity. It's a conceptual model. Right? So active acidity, it's the active H plus in solution, the active ion. And so we refer to this these ions moving around, these H plus, is active acidity. It's not concentration per se, as I mentioned before. Again, the chemists keep reminding me it's really an activity, and it's not exactly the same as concentration. Good thing is that when concentrations are low, it approaches activity. Okay, so that's just I have to put that in there so that the chemist won't beat me up. Now, the second pool we think about, exchangeable salt replaceable acidity. That is what we can push in with a salt and just exchange, a simple cation exchange reaction. So what do we get out when we push this out? We get exchangeable aluminum plus 3, exchangeable aluminum hydroxyl, AlOH plus 2, and the AlOH, 2 of them, plus 1, and H plus. So these are the versions of exchangeable aluminum that we get with salt replaceable acidity. And so you know that when we push out aluminums, we generate H plus. And when we push out aluminum OH plus 2s, we generate H plus. Okay? Salt replaceable, replaceable by a simple salt, maybe KCl, barium Cl. And then the third pool, this huge monster pool, we talk about residual acidity. And it's these are various concentrations, the combinations of these polymers, AlOHX, a whole bunch of them, to some degree of charge. And these are polymers, and they're held strongly by organic matter and silicate clays. We talk about residual acidity. This very large pool of rather complex aluminum hydroxyl polymers bound by organic matter and silicate clays. How do we get them out? A simple salt won't do it. We've got to use something strong, usually a high concentration of barium acetate, which is not a neutral salt. Acetate breaks down, and we have not breaks down, but produces hydrogen ions from the acetate anion. Okay? So to get this material out of these strong bound places, we use something a little stronger, and this is barium acetate with adjusted pH. So now let's kind of think about those pools in pictures, right? So here is a picture of hydrogen aluminum ions in solution, okay? And this is what we think about active acidity. This is freely floating about in solution. They're not bound. They are free to move around. As they approach colloids, they are adsorbed, attracted to the exchange sites, right? So this active acidity is a very small pool of just material, H plus and aluminum in solution, floating around, not bound to anything. As we get toward the colloids, okay, we get into the salt replaceable. These are the exchangeable aluminum hydrogens and everything else. Right? And so these are adsorbed, associated, attracted to the colloid surfaces, exchangeable, salt replaceable. That's our second pool. As we get very tightly into inner layers of clays and tightly bound humus moieties, that's the residual. Right? So we have this pool of residual, which takes an extraordinary amount of effort to get, in terms of got to really push some chemical power into that to push it out. Very tightly held, a big pool. We have this salt replaceable, which is exchangeable, associated with these surfaces. And then we have in solution. So here's our this is a picture of our 3 conceptual pools: active acidity, salt replaceable associated with the colloids, and then humus and clay bound residual acidity, the 3 pools. And so active, salt replaceable, residual pools. So now here's a picture of a pH meter, right? And so the question is, I've got a cell sample here, I brought it in. Which pool does this capture? I measure the pH, I put my little wand in. You'll do this week. And you have a pH meter. What pool, which of these 3 pools are you measuring when you use this pH meter? Active, right? So this is the pool that's very active out in solution. You're measuring hydronium ion solution, translate to some electrical impulse, and you get a reading that's associated with the pH, or the concentration, the negative log of the activity. Okay. Active. Okay, now the last thing you're going to do in lab this week is you're going to do a titration, right? And so you're going to do an extraction. We've got a barium acetate extraction, collect everything, and then we're going to titrate it to see what the acidity is in here. And after we titrate it, we'll know one of these pools very nicely. So the question is, I drip through this barium, and we do this experiment, we drip it through, we titrate it back to find out the zero charge little phenolphthalein. What pool are we sampling? Deja vu all over again. Right? This is probably one of the greatest albums out of my era when I was a teenager and making music or trying to imitate music. But deja vu, we've seen this before. We've seen this before. So what happens when you add 0.5 normal barium acetate to soil? That's the question. What happens? And we're going to drip it through. So here's a picture, right? Here's our barium acetate, and we've seen this configuration before. So we leach it through. Okay? We push off all these nice little adsorbed ions, and we replace them with barium +2. Right? And the accompanying anion is acetate. So acetate is acidic, and it generates H+. Acetate removes the residual H+. Right? This is this big, very high concentration. It's actually getting to the residual pool. So quite different than the active pool. And when you have H+ along with acetate, what do you call that? Acetic acid. Right? How do you measure the H+ in acetic acid? You titrate it with a strong base. We're titrating this week with ammonium hydroxide, 0.1 normal. And we're going to add that to this material we've drawn out of the soil. And eventually we'll get water and sodium acetate. When this happens, we get the zero charge, phenolphthalein goes red. And it says, we have now neutralized it. So we are measuring by this titration with sodium hydroxide in our extract of barium acetate through the soil, we are measuring this residual pool and also some of the exchangeable. Phenolphthalein turns red, and you'll see that when you get the red color. Your lab instructors this week will show you about when that occurs. They'll titrate a blank just with barium acetate alone to show you when that happens. And so that's the subject of this week's lab. Pretty amazing. You haven't done chemistry probably since, if you were here with one of our chemistry instructors, maybe it was Dr. Neal, maybe it was, I don't know, or maybe you did at community college, but now it's time to come back and remember all this stuff. And so then we start to think about soil itself as a buffer, kind of a different idea or a way to interpret soil. Okay, so let's think about this. Here's going back to our picture again, right? Here's our active acidity pool, our salt replaceable pool, bigger, and then our monstrous pool, the residual. Right? This is huge. This just blows everything out of the water. So this is like my wallet, the active acidity. The salt replaceable, this would be equivalent on a good day to my bank account. And this residual, this would be equivalent to my entire vault at Key Bank, which of course I only have a little piece of at this point in my life. And so it's interesting to note that there's a dynamic equilibrium among these three pools. And so the question is, this stays, active acidity attempts to stay relatively constant. And so it's a very tiny pool. It's a smidgen of the total acidity. So what happens if you try to neutralize these? If you just had to neutralize these active acidity, these ions, and a couple teaspoons of lime would do it. But you take one out, neutralize it, and there's an equilibrium among these three pools. So as you try to reduce this pool, you get a reaction pushing from the bigger pool to the smaller, right? You're increasing the concentration, so it drives things to the right. And the more I take out, and I've got a seemingly inexhaustible pool, I can keep replacing these and keep this relatively constant. Kind of neat, right? So this is why pH is relatively stable, okay? Because of this dynamic equilibrium among these three pools. And then, as the salt replaceable starts to get drained, there's a huge pool in the residual that feeds this. So as you take one out of here, there's a whole line of ions waiting in line to move to the right. Okay? So in order to effect a change in this pH, in order to effect that change, you have to counteract all of these acidic aluminums and hydrogens here. So that means instead of just a couple teaspoons of lime, you're looking at tons of lime, because you've got to take care and neutralize all of this just to change this pH. And that's all due to this dynamic equilibrium among the three pools. So you can consider then soil as a buffer. Right? This pool, active acidity, is buffered because of this dynamic equilibrium with the residual pool and with the salt exchangeable, salt replaceable. And that's the story of pH. It tends to stay constant, and it takes a lot to change it. This is a buffer. The definition of a buffer, a system that resists change. We're talking about pH. So when we view this as a buffer, the system that resists change in pH. That's kind of the way we define a buffer. And this is a perfect buffer, right? This is resisting change in pH, the active acidity pool, compared to the bigger pool, exchangeable, compared to the huge pool, residual. Keeps feeding to the right until we take care of all of it. How does it work? Remember, dynamic equilibrium. Drill that into your head. Dynamic equilibrium among the three pools. These double arrows indicating backward and forward direction. Residual, salt replaceable, active. Dynamic equilibrium, feeding, keeping this constant. Okay, so there's a simplified view with some words of three little pieces that just took me about 4 or 5 slides or 5 minutes to kind of go through. This kind of says it all. So pH, now we know we understand it. We kind of get a way to measure it. We understand how it changes. And then if we were trying to model it, we'd be interested in what are the major factors that influencing pH. We've already talked about factors that influence CEC, factors that influence aeration, factors that influence temperature. Now we're kind of moving down the line, and we'll talk about the factors that influence pH. And so let's start out with acid saturation. Okay, acid saturation. This is numero uno. And what is it? Okay. Acid saturation, the percentage of the cation exchange capacity accounted for by hydrogen and aluminum. Percentage of CEC accounted for by hydrogen and aluminum. Why is aluminum in there? Well, we went through a very detailed explanation of the role of aluminum in acidity. It generates hydronium by hydrolysis of water. So we count aluminum as part of the acidic cations. It's very acidic. It generates H+. And we can measure what proportion of the CEC is accounted for by those acid cations. We talked about something similar the other day when we talked about calcium saturation, right? The proportion of the CEC taken up by calcium. This is the proportion of CEC taken up by the acidic ions H and Al. Okay, same idea. Now there's another concept related to this called base saturation. Okay? So we either have acid cations or, quote, base cations. Not that they're bases in the sense that they're accepting, they're generating OH, but they're not acidic. And so base saturation and acid saturation add to 100. Right? It's either a base cation, quote, base cation, or an acid cation. So acid saturation is equal to 100 minus base saturation. So why am I harping on base saturation? You know, for decades, we used to think about it in terms of the side of base saturation, the non-acid cations. And most of the literature, up until about the mid-'80s and '90s, really focused on base saturation. And we still use it as a way to characterize soils. But we're really focused on is the acidic portion of that. And so acid saturation is just looking at it from perhaps a more realistic point of view, I guess. So it's acid saturation, like other saturations, it's expressed as a percent, part per 100. Okay? And if we take this word, percentage of CEC accounted for by H and AL, and we translate that to a formula, see percent acid saturation is equal to the concentrations, activity of hydrogen and aluminum, those two, over CEC times 100. Right? So here we're converting to a percent times 100. It's a proportion of the acidic cations, H and aluminum, as a percentage of the CEC. Pretty straightforward. So let's have an example. Right? So here's some soil data. We usually get things in centimoles of charge per kilogram. And here's H, these are lab data, hydrogen, aluminum, magnesium, of course that's +2, calcium +2, K +1, sodium +1. These are lab data on the concentrations. So for this particular data set, I have 2 centimoles of charge per kilogram hydrogen, 3 centimoles of charge aluminum, 0.2 for magnesium, calcium 1, K1, and sodium 2. So I've separated out the acid cations from the non-acid cations, or the base cations. Again, we're trying to think about this more as non-acid than base because they're not bases in the classical sense. So the terminology tried to shift away from the idea of using base cations. And the real way to think about these or discuss them is non-acid because they're not true bases. And so that's been a shift, and we're slowly moving that way in the past 20 years or so. So let's look at the CEC. Remember CEC, the sum of total cations absorbed. So here we add them up. There's 2 hydrogens, 3 centimoles of aluminum, 0.2 magnesium, 1 of K, 1 of calcium, 2 for sodium. The CEC, by definition, we learned last week, the sum of exchangeable cations. Voila, we add that up, 2 and 3 are 5, 5.2, 6.2, 7.2, 9.2. So the CEC for this particular lab, these lab data, is 9.2 centimoles of charge per kilogram. You're familiar with this, centimoles of charge per kilogram, that's our SI unit. The acid saturation, next we build on that. So the H and aluminum as a proportion of the CEC, and here we just plug this into the formula, 2 for hydrogen, 3 for aluminum. We're multiplying by 100 to convert to percent and dividing by total CEC, 9.2. So here is our calculation, our formula to compute acid saturation for these lab data. So if we run that calculation, 5 over 9.2 is 0.543, multiply times 100, 54.3%. So there's the data showing us the acid saturation for this particular sample, 54.3%. And again, looking at that from the bigger picture. Right? Hydrogen, aluminum, proportion of total CEC times 100. And what am I trying to get at here? This should be, you're starting to get used to my dad jokes by now. Or not. Base saturation. So I co-opted a base and I made the base. So what's that equal to? 100 minus acid saturation, right? So remember, we either have non-acid cations or acid cations. We used to call them base cations, we still do, but more appropriately, we call them non-acid cations. The sum of acid cations and non-acid cations is equal to the total CEC. Right? So 100 is the sum, so 100 minus acid saturation is equal to what we used to call base saturation. And vice versa, 100 minus base saturation is acid saturation. Pretty straightforward. And you can see how that is, right? We have the total CEC, and you either have acid cations or base, non-acid cations, base cations. A picture. Here we have CEC of 21, an acid saturation of 14%. So you can see it's dominated by calcium and only 1 aluminum. So you run those numbers, and that's 14% acid saturation. The pH for this is 5.1. We take that CEC, same CEC, and we jack up the acid saturations to 62%. You see a lot more calciums. And look at what happens to the pH. pH drops. So this is a pretty good example of the impact of acid saturation on pH. As you increase acid saturation, you decrease the pH. It's much more acidic. The more aluminums and hydrogens you have taking up, the more acidic, the lower the pH. What happens if I change the CEC? And now I have CEC 9 and an acid saturation of 78%. Okay? So it's the acid saturation driving it. It's not the CEC. Right? So the important number for pH is acid saturation. How much of those are taken up by hydrogen and aluminum? Here's CEC of 9, and we'll do the same thing. We have acid saturation of 33 versus 78. Higher acid saturation, lower pH. Driven by acid saturation, not really driven by pH. So we could think about you probably don't know what this is, right? Because back in my day, when we used copious amounts of coffee, we had these big old percolators, right? And so you drip the coffee into here, and then there's a little indicator here, so you know how much coffee it is. So you could we'd serve up a bunch at a pancake breakfast or so. And so this configuration actually is quite remarkable to represent active acidity, a very small pool, and the exchange and residual. And so if I were just to draw this down, I would run out pretty quickly. But what happens when I turn this lever, right? This goes to reach equilibrium, and in order to move this down, I've got to move this entire pot down. Right? So it's kind of the same idea as buffer capacity. This is an indicator, maybe if it's active acidity, and to drain this, I've got to get rid of all of this behind it. And so this is another way to think about it, the percolator, or the model, the coffee model for buffering, and how much buffering capacity it takes to move the needle on active acidity. Silt loams, high CEC, would be represented by these, right? A sandy soil, lower CEC, you'd have a smaller vessel. So way to think about the impacts of texture, which affects buffering capacity because it affects these CEC and the storage capacity. So another way to visually think about this, the impact of texture on buffering capacity. Now, you've got a huge buffer in finer textured soils and a very small buffer in coarse textured soils. And one thing that we close with is we talked about colloids that can have a net positive charge, and I talked about this a couple of times. Right? Kaolinite, iron aluminum oxides and hydroxides, non-crystalline silicate clays. And so now we just talked about acidity, and we can make a much more direct connection with the conditions where these colloids can have a net positive charge. And which conditions? And you'll remember we talked about high acidity, low pH. And here's an illustration of this for net zero charge and low pHs and high pHs. Right? This is kaolinite. And so as you get into very acid conditions, we talked about a net positive charge. Okay? And there's this point, the isoelectric point, where it pretty much balances out. So this is the reason for the range in CEC on these types of colloids, kaolinite and iron aluminum oxides and hydroxides. Acid conditions, we actually have a net positive charge, reinforcing what we talked about last week. Low pH. So acid saturation. Next, type of colloid at the same acid saturation. Acid saturation is numero uno. And it turns out when we look at some of these colloids, the pH of smectites at a given saturation will be less than the pH of organic matter, will be less than the pH of the one-to-ones, kaolinite, less than the pH of oxides. So type of colloid makes the difference at the same acid saturation. They have different capacities to hold on to iron aluminum. Going down the list, what affects pH? Adsorbed cations. This shouldn't be a surprise after we looked at sodium and calcium. So sodium's kind of interesting. When you have sodium and you dissolve it, it results in a higher pH than calcium magnesium. It really generates a lot of hydroxyls. So we have sodium, we mix it up with carbon dioxide and water, okay? We end up producing sodium bicarbonate. And this is a prodigious source of hydroxide. So when all other things being equal, colloids dominated by sodium will have a higher pH than other colloids, than other cations, sorry. Parent material, limestone versus sandstone. Okay? Limestone, we talked way back at the beginning, calcium carbonate, magnesium carbonate, very rich soils, have a very positive impact on pH. They have induced a high buffering capacity because there's plenty of carbonate around. And so limestone soils versus sandstone, generally much higher pH. Well, I'm running out of time, and I've just about made it all the way through acidity. But we'll finish this up when I return, and you will deal a lot with this week with all this material. But this has been some 20, 30 years we've been doing these recording. And so I think it might be kind of neat to look in the background and see what's actually going on. Where am I? And so I want to take you through a little tour through ESF TV, where this is all happening. There we are in the control room, and our ESF TV engineer, Christopher Becura, is showing us some shots of the complex machinery that's used in the electronics to make this happen. In the old days, it was just a kind of a one camera and be walking around, and this has evolved over some 20 years. So it's a rather remarkable evolution. And this, if you could have seen it 25, 30 years ago, this would blow your mind.
So Tom, this is where you really are right now.
So here, so you see it's green screen? This is it. This is the essentially.
And this is what you see.
This is what I see. So I'm here in this downtown subliminal subterranean studio in Moon, and this is what it looks like when I'm just sitting here without all the electronics bringing up these beautiful views. So rather remarkable. This is the first time we've shown you the insides or the guts of ESF TV. So I hope that little foray was interesting. And again, to see this evolve over some 25 years, it's just phenomenal compared to where we were when I first arrived here at ESF and when Christopher Becura just came on the scene as the new TV guy.
All right, well, thank you everybody, and we'll wrap this bad boy up.
Well, that concludes our lecture on soil acidity. I will be back late Sunday night, but you'll be on your way to break. So the next time we see each other will be Monday, and for our last set of lectures. So I hope you have a safe trip back and have a wonderful break. And I look forward to seeing you at that time. And maybe I'll have some good tales of Turkey, not Turkey Thanksgiving, but Turkey the country to share with you. It'll be a remarkable experience going to this energy conference. Have a great day.